So this work that I will present was done in collaboration with Santiago Cifuentes, Samson Wang, Mario Berta, and Leandro Olita on quantum computational complexity of matrix functions, if you want to check out the paper online. So I guess this problem of computing functions of matrices doesn't require a lot of motivation, because there are many problems that can be formulated as enacting a function onto a matrix. So the very problem for quantum computation, the problem of Hamiltonian simulation, can be seen as exponentiating the matrix representation of the Hamiltonian. So, but this is not the only one. If the is with a real exponent, then we can use this function to prepare ground states. Linear system solving can also be seen as inverting a matrix, and also sampling from a hard distribution can be seen as monomials of a transition matrix, a Markov chain. So this problem gained even more attention with the advent of quantum singular value transformation, which is a framework that allows you to design algorithms to implement virtually any function of a matrix. So in this framework, you design your circuit in a way that all the parameters in that circuit depend only on the function, and then you can input via some oracle any matrix, so you can compute the function of this matrix using the same structure of this circuit. And this allows you to design many efficient algorithms for many tasks, and in particular some tasks that are provably hard for classical computers. So for example, the HHL algorithm for matrix inversion. But on the other hand, there were a couple of results in the direction of dequantizing QSVT. So these works, they prove that you can actually provide, given some special access to the matrix in a classical computer, you can actually provide efficient classical algorithms for the same tasks as QSVT. But this is this work for particular regimes, so for matrices with low rank or for estimation problems with constant precision. So then we wonder, the obvious thing to ask here is, where is the line separating quantum efficient algorithms but classically hard problems from these problems that you can provide efficient classical algorithms? So in this case, we might ask, what are the classes of matrices and also the functions that provably provide you problems that are hard for classical computation? So in this way, we can know where to find quantum advantage for algorithms built with quantum singular value transformation. So in how to gain insight on these possible speedups. So on one hand, we can use some complexity arguments to prove that the problems are classically hard. And if we provide also an efficient quantum algorithm for the same problem, then we prove that this is efficient for a quantum processor. So this problem is a BQP complete problem. On the other hand, we can investigate if we can just propose efficient classical algorithms for the problem. So if we can, then it's probably an easy problem for a classical computer. So in this work, what we provide is a catalog with a bunch of problems for different functions, different characteristics of the matrices, and different access models also for the matrices. Because one thing that I didn't mention is that QSVT depends on inputting an oracle for your matrix. So maybe the algorithms They are designed, they are efficient, but because the complexity is hidden in the design of the oracle. So here we consider also the problem of how to access the matrices. And we show results in both ends, also in the hardness and also in the classical easiness of problems. So let me be specific about these problems and the parameters that we consider. So specifically, we only consider Hermitian matrices. So for Hermitian matrices, applying a function to them is equivalent to performing eigenvalue transformation. And to make a fair comparison between classical and quantum, we consider that both have the same type of input. So both have some classical input, some classical description of the matrix, and both will output the same classical number. So for the input, we consider two models for accessing the matrix. So in the first one, sparse access model, you are given an efficient to compute function that given a row, you can find all the columns, all the addresses of the non-zero elements. So your matrix is sparse, so only a few elements are non-zero, and you can efficiently compute the location of these non-zero elements. And given the location of an element, of a non-zero element, you can also efficiently compute the value of this matrix entry. And the second access is the Pauli access, where you are given the matrix decomposed in Pauli representation as a sum of Pauli matrices. So for this type of access to be efficient, you need to have a matrix with a Pauli log number of terms. So this is important. So all the time I'm talking about efficient access to this data. So there's no complexity hidden in the oracle, in how you build the oracles. And for the output, we also consider two problems, very simple to formulate. So the first one is the estimation of a matrix entry of your function. Oh, there is no laser. With some additive precision. And the second one is when you use your function, your matrix function, to transform the zero state, and then you perform the simplest measurement that you can imagine on this state. It's just measuring in the computational basis the first qubit out of your n qubits. And as I said, the class of matrices is also important here. So we consider some properties that will be important to trace this line between classical and quantum. So the first one is the norm of the matrix. So we bound norms of this input matrix. And this is important because maybe by just inflating the norm, you lose meaning of the precision in your estimation. So we can bound the spectral norm, the one norm, or in the case of the Pauli access, we can bound the one norm of the coefficients in the matrix in Pauli basis. And why is this important for this delimitation between classical and quantum? Is because if you just design the set of all matrices with a bounded spectral norm, bounded by 1, for instance, the set of matrices that has one norm bounded by 1 is contained inside the set. So if you restrict to bounding the one norm, you are actually constraining your problem, restricting your problem even more. So you're checking in a different regime if the hardness or if the easiness of your problem remains. And another thing that we consider is the sparsity of this matrix. So in the computational basis, in the sparse access model, we have the number of non-zero elements per row and per column, S. And in the Pauli access, we have the number of Pauli elements in the decomposition. And also, I said it's a catalog with a lot of parameters to consider. So we consider a few functions. So monomials, time evolution, Chebyshev polynomials, and matrix inversion. So this might seem just particular examples of functions, but all of them can actually be used to construct other functions. So by studying them, you might guess some results about other more general functions. And in fact, we have some result for general functions. And the precision of the estimation is also obviously very important. If you have a very low precision, then you can just guess your result and you will be within that precision. And for each of these functions, we have some parameters that are specific to them, and we can also vary them and check if the problems are hard or easy. So for time evolution, we have the evolution time. Monomials and Chebyshev polynomials, we have their degree. For matrix inversion, the important thing is the condition number of the matrices. And this is not, obviously, it's not the first time someone investigates something like this. So many results were known before. So BQP completeness for Hamiltonian simulation, matrix inversion, and for monomials were known before. But in all of these cases, in restricted settings. So here we prove the same results, or not, for many different settings. And then we ask ourselves, what happens with these speedups? Do they remain when we toggle these parameters that I mentioned before? And there's another related result by Montanaro and Shao, where they show a separation between classical and quantum for matrix functions, but in terms of the number of queries to the oracle for the matrix without constructing this oracle and without talking about complexity class for the problems. Actually, they posted an update on their paper where they do talk about them, but okay. So results. Ta-da! This is the result. Digest it. No, you don't need to. So it's just a classification for all these possible combinations of parameters that I said in terms of their complexity class. So we can classify many of these instances as being BQP complete, being out of classical efficient classes, but in BQP or classically efficient. But better to look at this catalog in a more, just a soup of symbols. But here we have the functions, the different access models that we are considering, the different restrictions that we impose in the matrices, and what are the classifications for these problems. So just some, I will not go through all these results, of course, super boring, but I would like to just highlight some general results. So the first thing is that all these results for hardness of the problems, they hold in both access models. So you don't get any special power, at least in general, if you just decompose your matrix in Pauli representation, for instance. So all of them remain hard in the sparse access and in the Pauli access. And all of them have instances where they are BQP complete. And also, the two problems that we consider, the matrix entry estimation and the local measurement, they both have similar complexities. Also, these two problems, they are comparable. And more interestingly, there is a hierarchy between these functions that we considered. So if we suppress the norm of the monomial function, for instance, this problem already becomes classically easy. If we consider a reduced set of matrices, the problem is already easy for classical computers. While for all the other functions, this is not true. We can actually strongly suppress the norm. So if we take the norm, this k, if you can see, I don't know, this K is the norm of the matrices. So if we consider matrices with norm below 1 over polylog the dimension of the matrix, which is a very low norm, still the problems remain hard for classical computers. And this hierarchy is so strong that for monomials, actually, even a slight suppression in the norm of the matrix, or even a slight restriction on the set of matrices that we are considering, already make the problem classically easy. So if we consider a matrix with norm 1 minus some small constant, it's already an easy problem. And the last observation is that I said that the two access models, they have the same power. The problems are hard in both models, but actually it's not 100% true. You can gain advantage from the model depending on the structure of your input matrix. So changing the access model can make problems easy. So for instance, for all the functions in the sparse access, we have that the problems are, even for constant sparsity, the problems are BQP complete. But now if you take a matrix whose Pauli decomposition has only log n terms in it, this matrix is also a sparse matrix, possibly with constant sparsity. But you see that just because you changed your access model, then all the problems become classically easy. So exploring the structure of the matrices also matter for hardness, which should be expected. Okay, so just to give you a flavor for how to prove these things, I'll just give an example for the classical easiness and for the classical hardness. So for instance, if we want to prove that the local measurement problem for the function that we choose is matrix monomials, given that we have the matrix and Pauli access, if we want to prove that this problem is in BPP for matrices with Pauli norm below 1 and precision and degree of the monomial in polylog the dimension of the matrix, what we have to do is to provide an efficient classical algorithm to solve this problem. But not only, we have to provide bounded error classical algorithm. So what we need to compute is the result of the local measurement, which is that number. And what we know is the composition of the matrix in Pauli terms. So in this case, it's actually quite simple. We can simply substitute the decomposition of the matrix into what we want to calculate. And this gives us this sum of expectation values of Pauli matrices. So each of these terms are efficient to compute in a classical computer. It's just expectation value of Paulis. We know that as we have order m Paulis being multiplied, the complexity, the runtime to compute each term will be the number of terms, m log n, which is the complexity for it. So, but then the number of terms might be too big for you to calculate each of them, but you can simply sample from this sum by using as a weight the coefficients for each term. And calculating the number of samples that you need for a given precision, you get that number. It depends on the Pauli norm. It's exponential, because m is polylog n, so this is in general a large sample complexity, so in general it's not efficient. But if lambda is below 1, then this is smaller than 1, so the number of samples is polylog n. So this is the algorithm. So we propose an algorithm. It is efficient, so we prove that this instance is classically easy. And actually, we could compute the runtime for calculating this sum exactly. So because if you multiply all the Paulis that appear in the decomposition, you don't get any number of Paulis. You can only get to the L of them. So in the end, you only have 2 to the L different terms in your sum. So the time to compute this exactly is given there, 2 to the L, the number of terms, times the complexity to calculate each of the terms exactly. So in this case, you see that if the number of terms is doubly logarithmic with the dimension of the matrix, then even the exact algorithm is efficient. So you proved again some instance for which the problem is not classically hard. And an example now for how the BQP completeness proofs go. So let's consider again an example. We want to estimate the matrix entry of a monomial of a matrix. We want to prove that this is BQP complete if A is sparse with a sparsity constant, order 1, and if the precision and the degree of the monomial are both polylog with the dimension and with this condition on the one norm of the matrix. So for this, we have to prove that, first of all, the problem is as hard as BQP, so we can map any problem in BQP to estimating this matrix entry for a matrix that has exactly these characteristics, sparsity order 1 and one norm suppressed by 2. So a BQP problem, the BQP class, it's actually not the BQP class, but the promised BQP class is defined as this. So given a bit string, you have a circuit with polynomial size. And if you apply your circuit to this bit string with some ancillas, and if you measure the first qubit in this, you can say if X is in one set of bit strings, the yes set. If this alpha, this amplitude is squared is above 2/3, or if X is a null, then this alpha will be below 1/3. So we have to construct a matrix that encodes the circuit. And after applying the function, we have to prove that this information about alpha x1 is contained in the estimation of the matrix function, or of the matrix entry of the matrix function. And then this proves that the problem is BQP hard. For the membership in BQP, we just show an efficient quantum algorithm that can be built, for instance, with QSVT. So this mapping, this was used by Janzeng and Vokchan to prove exactly the hardness for this problem for matrix monomials. So you just double your circuit and put a Z gate in the middle. So this is the circuit, and then you apply each of the gates in the circuit controlled by one clock register. So you start with your clock in time 0, and then your bit string is in X. This is the input. Then by applying this to 0x, you get that the time register is updated to 1 while you apply the first gate to X. And so on and so forth until your clock register is in time M, where M is the total number of gates, and you applied all the gates to the bit string. So all the gates of the circuit are contained in this matrix, and it is a Hermitian matrix. It's possible to show that this matrix has one norm bounded by 2, and that its sparsity is 4 or 8. No, I'm not sure, but some constant number. Now we can simply do spectral decomposition of this matrix, apply the function to it, and calculate the matrix element we are interested in. So we can do it, and actually we can do this for an arbitrary function. Once we have the spectral decomposition of our matrix, and we can simply apply any function to this spectral decomposition, and we see that the matrix element contains information on alpha x1, but maybe this information is just too small to detect when we estimate this matrix element. So it could be the case that this part here that depends on the function is just either 0 or too small, or smaller than your precision, such that you cannot tell what the value of alpha is when you estimate the matrix element. So, but with this, we have a sufficient condition to say that a function is BQP, not complete actually, BQP hard. So if our precision is some omega k for any k polylog, and then the matrix satisfies this, the sparsity is constant, and the one norm is bounded. If there is an m, also polylog n, for which that term that accompanying that goes with the alpha, the information about the circuit, if this number is larger than our precision, then this function is BQP hard. And this is a nice thing because for these are the eigenvalues of that matrix A, and these are exactly the extreme points of the Chebyshev polynomials. So for Chebyshev polynomials, each of these f terms in the sum will be 1, so they will actually add up, and you can prove that Chebyshev polynomials are hard to estimate, even for constant precision. So that's it. Just some final comments. So QSVT is very powerful, but it's not for everything. It's not every problem that you need to apply this powerful tool. So we just investigated where it makes sense to apply this tool, where we gain some quantum advantage. So we show that access to the matrix, some matrix properties, sparsity and norm, the precision of their estimation, which kind of function you are dealing with, all these things, they matter when deciding on the complexity. And then the obvious thing to think for further work is, what about other functions? So can we apply this general result to other functions that will give interesting results on hardness? Or can we further explore the structure of the matrices, as I showed for the Pauli representation? Are there other types of access that give us some quantum advantage while having the problem classically hard, but accesses that also make sense for a classical computer? So that's it. And before finishing, I would just advertise that if you don't know, Technology Innovation Institute, we are in Abu Dhabi, United Arab Emirates, and we have a quantum research center there. We do quantum computing hardware, superconducting qubits, quantum sensing, quantum communication, some fundamental research, and then also we do quantum algorithms, and quantum algorithms group is hiring. We need some junior postdoc. And so if you are interested, this is an immediate hiring. You can just check out our activities in the link, and you can also reach out to me if you are interested. And that's it. Thank you for your attention.
So we can take a few questions.
Thank you for a very interesting talk. I'm interested, is there any trick what we can do if the matrix A is not Hermitian?
This I should have also put this in the future investigations. I actually don't know. You could think, like for the algorithms, for the inclusion, probably you can just use some QSVT. But actually, even for this part, for the inclusion, you are restricted in the kind of functions that you can apply. Because you have some parity restriction and so on. But, well, we were looking at the problem from the perspective of Hermitian matrices, but maybe we could have just stopped, because for constructing this mapping from circuit to the matrix, we have to take the Hermitian conjugate of our first construction that just applies the gates controlled by the clock. But yeah, maybe if we just stop there, we can analyze the hardness and see some result. Because actually the spectral the composition of this matrix without the other part is similar. So we do have the spectral decomposition. We could have tried. I don't know why we didn't.
Thank you.
But yeah, in any case, you have to see what are the properties of this matrix. So you say, yeah, this instance with these properties is hard or not.
Nice talk. Same follow-up question. So I think the circuit to the hardness reduction, you have used a technique similar to the HHL paper.
Yeah, there they use a bit different
Yeah.
clock construction, but yeah, it's similar.
Yeah. So I was just wondering on the same line, if we have in HHL, if the matrix is not Hermitian, then they do the embedding of to a Hermitian block like, and then they proceed, or all the result of the paper holds. So can we think in that way also here for non-Hermitian cases, or there will be a problem?
In their case, they do this embedding in a Hermitian matrix because their algorithm needed the matrix to be Hermitian, I think. So yeah, so the hardness, I need to think more about it, but I think for the hardness, we don't need to impose that the matrix is Hermitian.
So just continuing with this, we can do block encoding and have the Hermitian matrix, also have a non-Hermitian matrix in a bigger Hermitian matrix, and then can we do the same thing with your...
Yeah, also this could be a possible trick. But then I don't know if because the embedding has to keep the properties of the circuit, I don't know if you would have any problem, but yeah, this is a possibility.
I think spectral decomposition, which means we can have Chebyshev polynomials, so we can decompose the non-Hermitian in the terms of Chebyshev polynomials and go ahead with it, maybe, I don't know.
Yeah, but then, okay, so you have to think of the algorithm that you will use to prove the inclusion also, because then what QSVT does, at least, is to implement the function to the singular values. So in the end, you are implementing the function to real variables. So, but there are other things using the inverse function that I think they work for, also for complex variables, so you could think of functions directly.
Yes, maybe.
Yeah.
Thank you. Thank you.
But for the inverse, particularly, the singular value transformation works as the inverse already, so you don't have to worry.